I welcome you all in this video. In this video, we are going to discuss about multivariable differential calculus. The content of this video is we are going to discuss partial derivatives, directional derivatives, and few of their properties. First, we are going to see what is partial derivative in multivariable calculus. Here we are going to take an open set from Rn and a function f from S to R, which is a real valued function. That is, if we take any open set in Rn, that is n tuple x1, x2, etc., xn, the value on f that is f of x1, x2, etc., xn is a real value. So we are going to take such a real valued function. Now we ready to define a partial derivative of this function f. Suppose if we take the vector x, n tuple, x1, x2, and so on, xn, and c vector is equal to c1 and so on, cn, and if xi equal to ci for I not equal to k and xk not equal to ck, then limit xk tends to ck, f of x minus f of c. Here this is x vector, c vector divided by xk minus ck is called partial derivative of f with respect to xk. And here we denote this partial derivative by dk f of x. So R f kth derivative of c vector. It is not the kth derivative, it is a derivative with respect to a kth variable. Next, we are going to see what is directional derivative. So as usual, we are going to take a function f at c. C as we defined in the earlier one, that is n tuple c1, c2, etc., cn. In the direction u, the directional derivative of f at c in the direction u is denoted by f prime cu, which is defined by f prime at the point c with respect to the direction u is limit h tends to 0 f of c plus hu. Here we are going to differentiate f at the point c in the direction u. Divided by h. Whenever this limit exists, we can say f, the directional derivative of f at c in the direction u. Next, we are going to see a few properties of directional derivative. First one, whenever we are taking the direction 0, then in this definition we get the term h u is also 0, and we are having h not equal to 0. So what we get? F prime at C in the direction u exists. So here h not equal to 0 and this term becomes 0. So anyway, the whole term exists. This exists for every C belongs to S. And the second one, if we consider kth unit vector, that is uk equal to, that is the kth element becomes 1, the rest of the elements are 0, where 1 is in the kth place. Then the directional derivative of f at C in the direction uk is limit h tends to 0 f of C plus h uk. So the same definition we are going to use here, but with the direction uk. Minus f of C whole thing divided by h. So here f prime C uk is called the kth partial derivative, and it is denoted by dk f of C. So this is kth partial derivative. Next one. So in case of the real valued function f from n-dimensional space to R, the above definition reduced to the usual partial derivative, that is dou f by dou xk, that is if x is equal to x1 etc. xn, let f of x is equal to f of x1 etc. xn. Hence limit h tends to 0 f of x plus h uk minus f of x whole thing divided by h becomes limit h tends to 0 f of, here x is x1 etc. x k plus h etc. xn minus f of x1 etc. xn divided by h. Here xi not equal to xk for all I taking the value 1 to etc. n. Now limit h tends to 0 f of x plus h uk minus f of x divided by h is the normal partial derivative dou f by dou xk. So whenever we are taking a real valued function, the partial derivative is same as the usual partial derivative. Now we are going to see the next property, which is if f is a mapping from n-dimensional space to m-dimensional, which means or f is m tuples f2 etc. fm, then partial derivative of f at point C in the direction u exists if and only if the partial kth derivative of f at the point C with respect to the direction u exists for each k is equal to 1 to etc. m. That is partial derivative of f at the point C in the direction u is, the directional derivative of f at the point C with respect to the direction C is the partial derivative, that is the derivative with respect to the first variable at the same point C and the same direction u and so on. So that is the directional derivative at the point C in the direction u is the partial derivative with respect to the first variable at the point C in the direction u and so on. The partial derivative with respect to the mth variable at the same point C with respect to the direction u. So this is equal. So this is here we have to note down the directional derivative exists whenever the partial derivatives exist. So for that, we know that the directional derivative is defined in this way, that is limit h tends to 0 f of c plus hu minus f of c divided by h. And here we know that the directional derivative of f is the partial derivatives with respect to all the variables. So here we can rewrite limit h tends to 0. This is f1 c plus hu minus f of c by h and so on. Fm c plus hu minus fm of c by h. Since each fk, that is k takes the value 1 to etc. m, is a function from Rn to R, we have directional derivative of f at the point C with respect to the direction u is derivative with respect to the first variable at C in the direction u and derivative with respect to the second variable at C in the direction u and so on. The derivative with respect to the mth variable at the point C in the direction u. In particular, if we take kth unit vector in the above property, so we will have the directional derivative of f at C in the direction uk equal to derivative with respect to the first variable and so on, derivative with respect to the mth variable in the direction uk. So this is for kth unit vector, the directional derivative of f with respect to the point C in the direction uk. And here we have defined derivative at the point C in the direction u. Our next property is, suppose if we take capital F of t is small f c plus tu, here t is scalar, then we will have derivative of f at the point 0 will be derivative of small f at the point C in the direction u. So we are going to prove this property now. For that, we are going to take, we just consider derivative of f at the point 0. So what will we have? Limit t tends to 0, f of t minus f of 0. We are going to find the derivative at the point 0 divided by t. So which is here we know that this f of t is small f c plus du. Now we can rewrite this as f c plus du minus f of c divided by, because here f0, when we substitute 0 here, this term becomes 0. So f of 0 becomes small f of c divided by t. So we know that this is our directional derivative at the point C in the direction u. So now we reached that the derivative of capital F at the point 0 is equal to directional derivative of small f at C in the direction u whenever we are having this definition. Next one, suppose if we are having small f of x is norm x square. So again we are going to take n tuple. Then we will have f prime of 0 is equal to directional derivative of f at the point C u, which will equal to twice C. So we are going to prove this now. So we start with the definition. F of t is this much. So f of t is taken as f of c plus tu. And we use this definition. So we will have this is norm C plus du, and this is inner product C plus du comma C plus du. So by using the definition of inner product space, we will have this is inner product C comma C plus inner product C comma tu. Then inner product T u C plus inner product tu T. So this is inner product CZ becomes norm C squared. And this term using the properties of inner product, we will have twice TCU, and the last term becomes T squared norm U squared. So continuing this one, we will have now differentiate with respect to T. So what will have first term, we are not having T, it is independent of T. So when we differentiate this with respect to T, this becomes 0. And here we are having T with respect, when we differentiate this with respect to T, we get twice Cu, and here 2 times T norm U. So now we had first term becomes 0, second term twice Cu, last term becomes twice 2 norm U square. Now, in the previous property, we have proved that f dash of 0 equal to small f dash C comma U. Here it is equal to, when we, this is f dash of T. So when we substituting here f dash of 0, substitute T is equal to 0. So what will we have? First term 0 already, the second term independent of T, so we will get twice Cu. The last term, if we replace T is equal to 0, this becomes 0. So finally we get twice Cu. So f dash of 0 is equal to f dash of C comma U. This is we got from the previous property. We know that f dash of 0 is now twice Cu. So this is what we need to prove. So the next one, we are going to say about the linear function. Suppose if we consider the function f from Rn to Rm, we can say this is linear if f of alpha x plus beta y equal to alpha times f of x plus beta times f of y. Whenever this property satisfies, then we call that real valued function is linear. So now we recap the definitions of derivatives and their properties. First, we can say a function, which is a real valued function. From S to R, where S is a subset of Rn, which is an open subset of Rn. And we can say that f is, we can define a partial derivative of that f with respect to the kth variable, which is defined by limit xk to ck f of x minus f of c divided by xk minus ck with the condition xi is equal to ci for I not equal to k and xk not equal to ck. The next one, directional derivative. The directional derivative of f at c is defined by limit h tends to 0, f of c plus hu minus f of c divided by h exists. Whenever it is exist, we can say f is has a directional derivative at the particular given point c in the direction u. And the first property, whenever taking the direction u 0, we get f dash of c comma u exist. And in the kth unit vector uk, we have defined the kth partial derivative of f with the definition limit h tends to 0 f of c plus h. Here instead of u, we have taken the kth unit vector uk minus f of c divided by h. Here we have defined, we have shown that whenever we have taken the real valued function f from Rn to R, then the kth partial derivative is same as the normal issue partial derivative. In the third property, we have taken the real valued function f from Rn to Rm. Then the directional derivative of f at the point C u exists if and only if all of its partial derivative exist. And here, whenever we are defining capital F of t, small f c plus tu, then we are having f dash of 0 is equal to small f prime cu. The same way, whenever we are defining f of x is norm x square, then capital F dash of 0 is equal to small f dash of c comma u, which is equal to twice cu. And the last one is linear property of real valued function. A function is said to be linear whenever it satisfies the condition f of alpha x plus beta y is equal to alpha times f of x plus beta times f of y. Next, we are going to see that if directional derivative of f at the point C in the direction u exists in every direction, all the partial derivative exist, but not the conversely. So here we have discussed the property already that if f from Rn to R, that is f is defined f1, f2, etc. f from n tuple, then the directional derivative of f at the point C u exists if and only if all the partial derivatives exist. So with that property, we can say whenever f dash exists in every direction, all the partial derivative exist. Now we have to show that the partial derivative whenever exists, but the directional derivative is not exist. So we are going to prove this with the example. Here we consider function f from R to R, which is defined by f of x comma y takes the value x plus y whenever x 0 or y 0, and it takes the value 1 rest of the cases. So now first we have to take we have to show it has all the partial derivative. Here we are having two variables. So the partial derivative with respect to the first variable, that is x, and we are going to check the partial derivative exists at the point 0. And the first partial derivative with respect to x is limit x tends to 0 f of x comma 0, we are going to check at the point 0 comma 0 divided by x. Now, using the definition, whenever we are having either x0, y0, we will get x plus y. So this is x plus y. Limit x tends to 0, f of x comma 0 becomes x plus 0, that is x, and f of 0, 0 also belongs to the first case, that is x plus y, 0 plus 0 becomes 0 divided by x, so which will gives us 1. So the partial derivative with respect to x gives us 1, and we are going to check the same for with respect to the second variable, that is y. At the same point 0, which we will have limit y tends to 0, f of 0 comma y minus with the same point 0 comma 0 divided by y gives us the same, which is limit y tends to 0. This is y plus 0 plus y gives y, second term 0 divided by y, which is also 1. So here d1, all the partial derivative exist. So we are having all the partial derivative exist. Now we have to show the directional derivative f dash c u does not exist. So this is what we have to show. Now we consider directional derivative at 0. So what will we have? First we consider f of at the point 0 hu, which is divided by h, which will give us, this is in the first case using the definition of f of x plus y, we will have this is f of hu, this is f of 0, if by the definition f of 0 becomes 0, then in the denominator we are having h. Now we take the direction u as a1, a2, with a1 not equal to 0, a2 not equal to 0. Then we have f of hu is f of h a1, h a2. So using the definition of f of x comma y, whenever either of the terms 0, it becomes x plus y. Otherwise, we will have 1. So this is none of them, HA1, HA2, both not equal to 0, since H is also non-zero. We will have the second case 1. So now we have f of HU is equal to 1. Now taking the limit, H tends to 0, f of 0 plus HU minus f of 0 divided by H is limit h tends to 0, f of hu by h. So here we are having f of hu is 1, which is limit h tends to 0. This is 1 by h. When we applying the limit h tends to 0, it doesn't exist. So thus we have shown that whenever all the partial derivative exist, need not to its directional derivative exist. Thank you.